In the last lecture, we had an introduction to the field of compressible fluid flows. We looked at the applications and definitions of compressibility. Today, let's review a very important topic in engineering, thermodynamics. We have seen in the previous lecture, an ideal gas follows the equation of state given by PV equal to RT or P equal to rho RT. And the assumption of calorically perfect gas allows us to assume that the specific heats are constant. As it turns out, that the perfect gas assumption is valid for a wide range of pressures and temperatures. We will use this assumption and the ideal gas equation extensively when studying compressible flows. Let's solve a simple example problem using the equation of state. A pressure vessel of volume 10 meters cube is used to store high pressure air for operating a supersonic wind tunnel. If the air pressure and temperature inside the vessel are 20 atmospheres and 300 Kelvin respectively, what is the mass of the air stored in the vessel? We are given the pressure to be 20 atmospheres, temperature as 300 Kelvin, volume of the vessel as 10 meters cube, and we need to find the mass of the air. We can compute the density of air using the ideal gas equation, which gives us rho is equal to P divided by RT. We can then substitute in the values to get the density of 23.54 kg per meter cube. The total mass in the pressure vessel can then be computed using mass is equal to density times volume, which gives us a mass of 235.4 kgs. And that's our answer to this problem. In this lecture, we will learn the following important concepts of thermodynamics: internal energy and enthalpy, the first law of thermodynamics, specific heat capacity, the second law of thermodynamics, entropy and isentropic relations, and finally a quick summary of the thermodynamics equations. Now let's look at some of the important definitions in thermodynamics. The internal energy per unit mass, denoted by letter E, is a macroscopic property of gas, representing the vibrational and rotational energy of the gas molecules. The enthalpy per unit mass, denoted by letter H, is defined as H is equal to E plus PV or E plus P divided by rho. Enthalpy is not a physical property. It is a variable introduced to simplify equations. Both the internal energy and enthalpy have units of joules per kg. For thermally perfect gases, that is without chemical reactions, the internal energy and enthalpy are functions of temperature only. Consider a system with a fixed mass of gas separated from the surroundings by a flexible boundary. Heat can flow across the boundary into the gas, say by conduction through the boundary walls. Let delta Q be a small amount of heat added to the system. Also, let delta W be a small amount of work done on the system by displacing the boundary, thus reducing the volume of the gas. In the process, the gas in the system gains internal energy. The first law of thermodynamics is an energy conservation equation written as delta Q plus delta W is equal to dE. The internal energy is a state variable depending on the initial and final state of gas properties. Hence, we use an exact differential dE to denote the change, while heat and work depend on the process or the path used to go from the initial to final state. Hence, we denote them as delta Q and delta W respectively. The work done on the system is calculated as force times displacement, which gives delta W is equal to minus PdV. Substituting this in the above equation, the amount of heat added can be calculated using state variables as delta Q is equal to dE plus PdV. The two equations in the boxes are mathematical descriptions of the first law of thermodynamics. The specific heat of a material is defined as the amount of heat added per degree rise of temperature, dQ by dt. Therefore, the specific heat at constant volume is dQ by dt when dV is equal to 0 and at constant pressure dP is equal to 0. From the first law of thermodynamics and definition of enthalpy, we get the specific heat at constant volume as Cv equal to dE by dt and specific heat at constant pressure as Cp is equal to dH by dt. It is easy to derive these relations from first law of thermodynamics and definition of enthalpy. Try it as an exercise. For a calorically perfect gas, the specific heats are constant, independent of temperature. We can therefore write E is equal to CVT and H is equal to CPT. When the air temperature is lower than 1000 Kelvin, it can be assumed to be calorically perfect. So, in many compressible flow applications, Cp and Cv can be assumed to be constant. Now let's derive important relations between the specific heats. First, let's define a new variable gamma as the ratio of specific heats. Gamma is equal to Cp by Cv. Differentiating the equation for enthalpy with respect to temperature, we get this equation. Now replacing PV by RT using the equation of state, we get this equation. And in terms of gas properties, we can write Cp is equal to Cv plus R, or Cp minus Cv is equal to R. Writing this equation in terms of gamma, we get Cp is equal to gamma R divided by gamma minus 1. And dividing by gamma, we get Cv is equal to R divided by gamma minus 1. For air, gamma is equal to 1.4 and R is 287 joules per kg Kelvin. We will use these equations in our next example problem. In the example problem with pressure vessel, calculate the total energy of gas stored in the vessel. We are given the temperature of 300 Kelvin and we computed the mass of air in the vessel before to be 235.4 kg. And now we need to compute the internal energy in the pressurized vessel. We can compute the total internal energy as mass times specific internal energy. For a perfect gas, we can replace E by CVT and use the relation for Cv to write in terms of gamma and R. Now we can substitute the values for mass, properties of air and temperature to get the total internal energy of 5.067 times 10 to the power 7 joules. So the pressure vessel has an internal energy of about 51 megajoules. Now let's review another important concept in thermodynamics, entropy, and how it relates to the second law of thermodynamics. The heat added to the system and the work done on the system can be done in many ways. We will primarily be concerned with three types of processes. Adiabatic process where no heat is added to or taken away from the system. Reversible process where there are no losses, such as a process where effects of energy dissipation are absent. And isentropic process, which is both adiabatic and reversible. In an isentropic process, the entropy of the system remains constant. Entropy is a state variable which quantifies the deviation of a process from a reversible process. The small case s is used to denote specific entropy, and capital letter S is used to denote total entropy of the system. The change of entropy can be calculated as ds is equal to delta Q by T plus ds irreversible, where ds irreversible is the increase in entropy due to friction or dissipative losses. For a reversible process, ds irreversible is equal to 0, otherwise it is greater than 0. Therefore, we can see that ds is greater than or equal to delta Q by T. If the process is adiabatic, that is no heat transfer, then ds is greater than or equal to 0. Equations 1 and 2 forms the second law of thermodynamics. The second law gives us the direction of a process. The process will proceed in a direction such that the entropy of the system and surroundings always increase, or at best remain the same. We can see from the definition of entropy that if a process is adiabatic and reversible, then ds is equal to 0. Such a process is called an isentropic process. Next, let's see how we can calculate the change of entropy. We have seen that the entropy depends on the heat transfer delta Q and the temperature. For reversible processes, we can calculate the heat transfer from the first law of thermodynamics as delta Q is equal to dE plus PdV, and also from the definition of entropy as delta Q is equal to TdS. Combining these two equations gives us TdS is equal to dE plus PdV. Taking a derivative of the enthalpy and combining it with the first and second law of thermodynamics gives us TdS is equal to dH minus V dP. Starting from equation 4 and using the equation of state, we get a differential equation for entropy in terms of temperature and pressure. Now, integrating this equation from state 1 to state 2, we can calculate the change of entropy S2 minus S1. This gives us an equation for calculating the change of entropy if we know the temperatures and pressures at two states. Similarly, starting from equation 3 and using the equation of state, we get a differential equation in terms of temperature and specific volume. Now, integrating this equation from state 1 to state 2 gives us another equation for calculating the change of entropy. This equation is useful when we know the temperatures and specific volumes or densities. Equation 5 and equation 6 are very important equations. These equations can tell us if a process can take place from state 1 to state 2. In other words, these equations give us the arrow of time. Now let's use the equations which we have derived to solve a problem. In the pressure vessel seen in the previous example, let us now heat the gas in the vessel. The heat is added until the temperature of the gas reaches 600 Kelvin. Calculate the change in entropy of the air inside the vessel. We are given the volume of the vessel as 10 meters cube, and we have previously computed the mass of gas to be 235.4 kg. As heat is added to the air in the vessel, the temperature of air increases from 300 Kelvin to 600 Kelvin. and the entropy of the air changes from S1 to S2. We need to compute the change in entropy as the air transitions from state 1 to state 2. As the volume of the vessel is not changing, V2 by V1 is equal to 1. We have the equation to compute the change in entropy using the ratios of temperatures and specific volumes. However, since the volume is constant, the second term is 0. Substituting in the values of air properties and temperatures, we can compute the change of specific entropy as 497.3 joules per kg Kelvin. The change of total entropy of air in the vessel can be computed by multiplying the mass of air, which gives us the change of entropy as 1.171 into 10 to the power 5 joules per Kelvin. And that's our answer. As we have seen before, an isentropic process is adiabatic and reversible. Therefore, delta Q and ds irreversible are 0. Hence, S2 minus S1 is equal to 0. We have seen this equation for calculating the change of entropy using temperatures and pressures at two states. Setting S2 minus S1 as 0 in this equation, rearranging the terms, and writing Cp in terms of gamma and R, we get this equation. Now, dividing both sides by R and taking the exponential, we get this very important isentropic relation between pressures and temperatures. P2 by P1 is equal to T2 by T1 raised to gamma divided by gamma minus 1. Similarly, we have seen this equation relating the entropy with temperatures and specific volumes. Setting the left-hand side of this equation to 0, and writing Cv in terms of R and gamma gives us this equation. Rearranging the terms gives us this equation, and now dividing by R on both sides and using the exponential gives us another important isentropic relation between density and temperature. Rho2 by Rho1 is equal to T2 by T1 raised to the power 1 by gamma minus 1. We can now combine these equations into a single equation relating pressures, densities, and temperatures in an isentropic process. You may have already seen and used these equations before in your studies on thermodynamics. Now you also know that these equations directly come from the mathematical descriptions of the first and second law of thermodynamics. The isentropic equations are very important in some of our upcoming topics in the subject of compressible fluid flows. Finally, let's summarize all the equations. You can take a snapshot of this slide for your future reference. Also, all the notes including this summary are available in the description of this video. Don't forget to get the lecture notes from the description. If I find any mistakes, they will be in the description. I'm using the feedback to decide format of the next lectures. Please let me know in the comments. Finally, I plan to put out videos more frequently going forward, so do subscribe to get notified.